Welcome back, everybody. Welcome to our final video in the series using Python in GIS. Today we are going to generate land surface temperatures, okay, from Landsat imagery. If you guys remember, if you all remember from last time, we generated a whole bunch of indices. Well, not a whole bunch. A few indices. We generated our vegetation index, our moisture index, and our burn ratio. And I promised you one last video on how to do a land surface temperature analysis. Okay? So that's what we're going to look at today. And I tell you what, this step, this programming probably pulled my hair out more than any other, and it wasn't the difficulty of the actual computations, because I've done it over and over and over by hand. It was how Python and arcpy work with each other and converting Unicode information into floating point data. And that was a little frustrating, but I'll show you how to do that so you can avoid the headaches that I had trying to solve that problem. For all you Python programmers, it probably wouldn't have been a problem to you at all. So anyway, so let's get started. All right, so again, last time we created a few indexes: the moisture index, the vegetation index, the NDVI, which we're going to actually revisit today for one of our steps. And we also did the normalized burn ratio. Again, you don't have to do that if it's an area that doesn't have any fire or hasn't had a fire. All right, so basically everything that we do today would be added at the end of our big long script, and it would be the last few steps that we need to do. Okay, so let's go over to our lst.py file and see what we got going today. All right, most of this is pretty much the same. It's making sure that I have paths and stuff set for all of my data. And I wanted to make sure that I'm pointing at the Indices directory for my output. And I want my input for all of the analysis here to be from my radiance directory, okay? Remember, we created that at the beginning of this whole series, right? And then I hard-coded the two bands that we will be using throughout the script. And that is bands 10 and band 11. And you got to make sure that you get them out of the radiance directory, because you want the radiance, not the reflectance, okay? So band 10 and 11 are the two bands that we're looking at. The first thing that you need to do is you need to calculate at satellite temperature. And that is the temperature that is received at the satellite for each one of those bands. Now, how do you know to figure, well, what temperature are we talking about? Well, all the temperatures are actually in Kelvin, and we need to input the Kelvin conversions into a formula for each band, so we can convert the Kelvin into degrees Celsius. Now remember, when you talk about Kelvin, you never use the word degree, okay? So we say Kelvin, and then you say degree Celsius or degree Fahrenheit, depending on what you're using. All right? So anyway, where do you get this Kelvin data from? Well, that is easily found and that is in the metadata for the satellite image. And it's down here at the bottom of the file. Here's the file. We go all the way down at the bottom, and you're going to see 2 lines for K1, and you're going to see 2 lines for K2. And these are the 2 constants for each band. So you have a K1 for band 10 and a K1 for band 11, a K2 for 10 and a K2 for 11. And what you need to do is plug these numbers into your calculations, okay? And I'll show you that formula here in a second. Now, these numbers in the meta files, I've looked at all different Landsat images, and these numbers are the same, okay? Now, if there's ever an instance that they do change, which I doubt they will, you can, if you wanted to, put these numbers, you know, when you go in and we read the text file and created the new database file, you can actually take these, have it read these lines in the text file and input this data into that satellite database file and then read from that database file if you chose to do that. You can do that easy. But we're not going to talk about that. We've done enough talking about text files. But anyway, you need to get the Kelvin data from the metadata. All right, and that's where you find them. You'll need 2 for band 10 and 2 for band 11. Okay, so that's where these numbers are being plugged in. So the formula for converting the Kelvin into Celsius is the K2. Now we're talking where each band is the same, it just has a different number. So let's say band 10. We take the K2 constant and we divide it by the log number of the K1 constant divided by the radiance of the band, and we subtract 1. Then we take that whole thing and we subtract 273.15, okay? And that is the conversion from Kelvin to degrees Celsius, all right? So if we take both bands are the same in terms of the formula, it's just that the input numbers for the Kelvin are different. So band 10, we have these numbers, the 1321, the 774, okay? But the last numbers are the exact same. And then we have band 11, which is using the 1201 and the 480, all right? So this line, these 2 lines here, do the raster calculation, okay? That's what we're calling here the arcpy spatial analyst float, and then doing the program here. And this is the input raster, which is the band 10 that we have signed right up here with this hard-coded line. So it does all the math and assigns that to band 10 at sat. That just tells me that that's the at satellite temperature for band 10. We do the same thing for 11. Then we save each one of those raster calculations to their own raster image at sat 10 and at sat 11. Reason why we save these to an image is because we're going to use these 2 images in our next step. And we want to take the average temperature of each one of these bands and put them together into its own image file. And that's what we have down here is at sat 1011. Okay, we are doing a cell statistics analysis in Spatial Analyst for averaging the 2 rasters. And that is done on this line right here. So I assign the rasters to in Rast 1 and in Rast 2, and we do the math right here. We make the call to the cell statistics right here, and cell statistics is the in Raster 1 and in Raster 2, and we're finding the mean, the average between the two, and this data tag that I have at the end just tells me to ignore any no data. All right, I know that's kind of backwards, but no data says look at no data. All right, so we only want to look at data. We don't want to look at no data. Then it does its math and writes to disk our new image file, which is at sat 1011. Pardon me. The next part of our analysis, now that we have the at sat temperature, we're using the average, we need to calculate a couple things. We need to calculate the proportion of vegetation index, and we need to calculate the land surface emissivity, okay, the emission of energy coming from the ground. All right. We'll call the emissivity LSE. We'll call the proportion of vegetation PV. The PV is dependent on our NDVI that we created a few steps ago. Okay, so that's where we're making a call right here. We're saying bring in this raster, this in Rast N, and make that equal to our NDVI image that we did previously. Okay? The formula for calculating first we do the PV, the formula for calculating the PV, it's the square of, we take the raster NDVI and we subtract the actual lowest value in that NDVI raster. Then we divide it by the difference between the maximum value found in that NDVI and the minimum. So we subtract the minimum from the maximum, and we divide that into the actual raster data minus the NDVI minimum. So this minimum is used twice in this calculation. Okay? Now, how do we get this NDVI min and this NDVI max? Well, this is where it pulled my hair out, but we got it solved. All right? The minimum NDVI is found by making a call called Get Raster Properties Management. And we are getting the raster properties of the input raster, which is our NDVI, and we specify the keyword minimum. And it will return a value to NDVI min variable. Now here's where it pulled my hair out. You would think this being a number would assign a number to this variable. It does not. It returns a result. Okay? And a result is not a number. It is a Unicode return of a value. So basically what you had to, and it took me forever to figure out, why isn't this a number? It's a number. No, it wasn't. Come to find out through some of the error messages that I got that it's Unicode. So the next step is to reevaluate that variable by just adding this line here, which gets that output value from this call, gets that value, assigns it to this variable in a floating point number. And that's it. It took me forever to figure that out, but that is the line that is going to save all the hair on your head right there. Okay? So remember, when you use the get raster properties and get information about a raster image, pixel size, you name it, okay? It does not return a number. It returns a result, and that result is in Unicode, and you need to convert that to the appropriate data type that you're going to work with, in this case, a floating point, okay? So hopefully that saves you a big headache. So that's what we do on these next few lines, is we get raster information such as the minimum value and the maximum value, and we assign those to variables and turn them into the kind of numbers we need. Then we come down and do the math. Remember our formula, the square and these numbers here. Okay, if you remember last time I split the numerator and the denominator up, well, I did the same thing here. I didn't really have to. I could have done it all in one line just like this, but I just wanted to make things a little bit simpler for myself for following how it was doing things. All right, so I created a numerator and a denominator, and I plugged in each part of this formula into each one of these variables for numerator and denominator. And then I use the spatial analyst divide method and plugged in those two variables. And then I did another calculation that calculated the square of the whole thing. Okay? So I could have done this a lot simpler by doing one line, but like I said, I was just trying to make it easy on my brain. So it does all the math for this calculation right here, for calculating the proportion of vegetation, and creates us a new image file, which is prop_veg, and saves that out to disk. All right, so now we have that raster. The property vegetation index is used in calculating the emissivity, okay? So up here we have the PV, but then we have the calculation that calculates the emissivity, the LSE layer that we're getting ready to create. And this is a simple math problem with two constants, and that's the 0.004 and the 0.986. And that is a simple calculation right down here, a raster calculation, by calling in those two numbers and inserting them in the correct fashion. This times the raster. Make sure you call the raster of the proportion of vegetation, and then you add the 0.996 at the end. And that creates the land surface emissivity layer. Okay? And once you have that, now you're ready to do the final calculation for land surface temperature. The land surface temperature is another long formula, which is found here. And that is the at-satellite temperature, which we got up here with at-sat 1011. We divide it by 1. Then we add the wavelength of emitted radiance, which for these bands, it's 11.5. That would be a constant, okay? Then we multiply that by another equation, which is the at-sat temperatures divided by this 14,000 380. Now, this is also a constant, and I'll show you where to get it. And all of the formulas that you see me using here are available at the USGS Landsat program website, okay? But this 14380 is actually taken from this formula here. And we are that 14380 is actually this P here. And this equals this formula, okay? And this formula is made up of other constants, such as the Planck's constant, which is this number in joules, the Boltzmann constant, which is this number here, and the velocity of light, which we pretty much all know, okay, which is right here. So if you do the math on all this, it turns out to be this 14,380, okay? Again, this is available at the USGS Landsat program website. So that's the formula that we're going to plug in for our last bit of computations. So I assign my @sat to be the @satellite image raster. Pardon me. And I assign the emissivity to its appropriate image that we created right up above here, okay? And then the LST, the land surface temperature, is equal to, and then we plug in the formula for computing that. And then we get a brand new image, which is our land surface temperature image. Okay? So we run this script, and we get this mess. All right, so here we have our NDVI that we calculated last video, and we use the input of what is the highest and what is the lowest value of all these pixels, which are actually right here, okay? We pull those using the get properties management method. That's how we got these out of there. And we applied that to our proportion of vegetation index, which is this image here. Now, funny thing is you look right here in this big glob of red right here, there's actually vegetation underneath there. This is actually smoke from the wildfire. The actual fire is actually burning about right here. So this is the proportionate vegetation. And then we use that as an input to get the emissivity, the land surface emissivity. And then that is used in conjunction with our @satellite surface temperature to finally yield us our land surface temperature. And that is what we have coded here. So in this entire scene, if I zoom out, because we're doing the entire scene, not just a study area, in this entire scene, our land surface temperatures range from 5 degrees Celsius, like this area here is 11 degrees Celsius. So it ranges from 5 degrees Celsius up to 106 degrees Celsius. That's the temperature of the soil, okay? And that temperature falls around in this little white spot right here because this is current fire, all right? So it doesn't actually get the temperature of the fire itself. It's probably blanked in that area, but in the area you're getting these high temperatures of 100 Celsius and up to 106 in this particular scene. So we made it through 7 episodes of using Python in GIS. A lot of it was really boring, and I really appreciate you guys sticking with this series and enjoying the series. I've seen some of you have liked these videos, and I really appreciate that. Basically, the next step is to just take this code that we just did and add it to the end of our larger version of our script that does everything, and make sure that your variables are consistent for your input. Make sure that you're making the right calls. But when I run this entire script from just unpacking that zip file or that tar file all the way to generating the land surface temperature, the whole script runs, the whole process runs in about 40 minutes. Now, if we compare that to doing all of this analysis by hand inside of Arc, you're going to spend pretty much all day doing this. Okay, so Python script is extremely powerful in automating all of those mundane tasks. And the cool thing is while this script is running, it's running in the background. You can go back to your ArcGIS or QGIS if you created a QGIS version of the script, and you can go work on other projects while this is running in the background. So Python is an awesome tool. Thank you for sticking with me for 7 episodes. Not a lot of exciting stuff going on here. Please be sure to subscribe to My Physical World's YouTube channel and hit that notification bell for getting updates on upcoming videos, and share and get the word out so other people can learn the importance and the usefulness of Python. Thank you again for joining me, and I will see you in the next video. Have a great day.